Okay, so this is from 2018. It's question number 2. It's a circuit problem. So what I want to do is begin by going over some background information that you will need to know to solve this problem. So the background information for this, I want to talk about Kirchhoff's 2 rules. So this will be important for solving this AP question. So Kirchhoff's 2 rules. The first one is called the Junction Rule, which we're not gonna use this in this problem, but it's important to know. And then the loop rule. So let's look at a circuit. So here's a circuit that is very similar to what we're gonna see in our problem. So we'll say this is 6 ohm and this is 3 ohm. And then over here is 2 ohm. And we'll say it's a 12-volt battery like that. And we're going to label the currents. We're going to say the current coming out of the battery. So we always define current as positive charge motion. So if you imagine a positive charge right here near the positive terminal of the battery, it's going to move away from the positive terminal, around through the circuit, and back to the negative terminal. So current is positive charge motion. This would also be I1, and then the current splits right here. And so we'll call the current going up here to the 6 ohm I2, and we'll call the current coming down here to the 3 ohm I3, and then back on this side of the circuit, we're back to I1 because the currents came back together. Now the junction rule, we can apply it right here. That's a junction. What's happening is current 1, I1, comes into this junction. It splits into current 2 and current 3. And the thing that must be true is I1, which is the current into the junction, must be equal to I2 plus I3. This is conservation of charge. The junction rule is a statement of conservation of charge. The total charge flowing into a junction must equal the total charge flowing out. And all current is charge per time, basic definition of current. Charge per time, which gives us, coulombs per second, which is what we call the amp. But the point being, charge flowing into a junction must equal charge out. That's the junction rule. Okay, loop rule involves voltage. So for any complete loop in a circuit diagram, so let's start our loops right here at this dot. So there's different loops we could make. There's going to be there's 4 different loops we could make in this circuit. Is that right? No, 3 different loops we could make in this circuit. So loop rule, what it says is voltage gain for any complete loop must equal the voltage loss for any complete loop. I'll write that down. Delta V voltage gain for any complete loop must equal voltage loss for any complete loop. This is a statement of conservation. So this idea right here, voltage gain equals voltage loss, this is conservation of energy. Oh, my pen is misbehaving. Conservation of energy. Because the fundamental definition of voltage is change in potential energy per charge. As a charge, let's look at a positive charge right here. As it crosses the battery, it's going to be gaining potential energy. So that's a voltage gain. And as the charge goes through the resistors, that's a loss of potential energy. Energy gain for any complete loop in this cycle, the energy gained must equal the energy lost. Voltage gain equals voltage loss. All right, so let's actually apply this. So let's do a loop. So 12-volt battery, If that's a 12-volt battery, the easiest way to do that is to say that the negative terminal is 0, the positive is 12. So if we focus on a positive charge crossing this battery, that's going to be a voltage gain. 0 to 12 is a voltage gain. So we'll say plus 12 volts. Okay, so we've crossed the battery. Now when we cross this resistor, that's going to be a voltage loss, and we can express that using Ohm's law. Ohm's law is delta V equals IR. So the voltage across this 2 ohm resistor is going to be I1 times the resistance times 2. The voltage here across that resistor is going to be I1 times 2. So we can express that over here in our, so we had a voltage gain of 12. Now we're going to say minus 2I1. That's the voltage across this guy. Now let's continue our loop. Let's go bottom path. You can't do both paths simultaneously. You cannot go top path and bottom path at the same time. So let's go bottom path. The voltage loss across this 3 ohm is going to be minus 3I3. And then we're back to where we started right here. Voltage gain must equal voltage loss. So we just wrote a really useful equation. So let's do another loop. So starting at our same point right here, we cross the battery again. That's a voltage gain of 12. We cross the 2 ohm. That's going to be a voltage loss of negative 2I1. Now let's go top path. We go top path, the voltage loss there is going to be 6I2, and then we're back to where we started. Voltage gain equals voltage loss, so it all adds up to 0. Last possible loop we could do, let's do a loop for this upper part right here. Let's start looping right here. Now, if you cross a resistor against the current, that's going to be a voltage gain, which should make sense because this point over here is going to be at lower volts than this point over here. So as we cross from the right side to the left side, we're moving to a higher electric potential. So we're gonna write this down as a voltage gain. So starting our loop right here, we cross this 3 ohm. That's going to be plus 3I3, just using Ohm's law, and then coming around the 6, we're now crossing the resistor with the current. That's minus 6I2, and then we're back to where we started. Voltage gain equals voltage loss. Now, these equations can be solved for any of the variables that you're being asked to solve for. It's just a system of equations. Okay, so that is Kirchhoff's rules. And I also want to review, before we actually get to the problem, this is going to be very helpful, I want to review RC circuits. So RC circuits, so here's a circuit that I just made up, very similar to what we have in the problem. Okay, so here's a 2 ohm resistor. Up here is our 6. And then down here, we're going to put a switch with a capacitor. So we call this an RC circuit because it has resistors and capacitor. So 12 volt battery again, plus minus. Let's call this point right here point A. Let's call this point up here point B. And then let's call this point right before the switch point C. And let's say this capacitor is 3 microfarad. Okay, so we're going to do some calculations here. So what I want to do is I'm going to ask the following question. So find the current at points A, B, and C. So our 3 labeled points. So what's the current here, which is basically the current going into that 2 ohm resistor? What's the current here going into the 6 ohm resistor? And then what's the current down here where the switch is located, the current flowing into that switch? So the current at points A, B, and C, 1. We're going to do this immediately after switch closes. And then we're going to do it again for a long time after switch closes. Oh, and I want to specify this capacitor is initially uncharged, which is important. So there's no charge on that capacitor at the beginning of this situation when the switch closes. Capacitor starts uncharged. Now, let's just go with that thought. What's the significance if this capacitor starts with 0 charge? Well, okay, what's our fundamental definition for capacitance? So capacitance, like this C right here, what does that mean? The basic definition for capacitance is charge over voltage. And this gives us the unit of farad. So charge is measured in coulomb, voltage is measured in volts. A coulomb per volt is a farad. So for example, 3 microfarads, that's 3 times 10 to the negative 6 coulombs per volt, which means if you have a potential difference of 1 volt across this capacitor, you're going to have 3 times 10 to the negative 6 coulombs. If you have 2 volts across this capacitor, it's going to be double this value. You would have 6 times 10 to the negative 6 coulombs on that capacitor. All right, so if this capacitor is initially uncharged, let's back this up, we don't need this. So if this capacitor is initially uncharged, what would be the voltage across it? Well, if the charge is 0, how many volts are going to be across that capacitor? So rearranging this equation, voltage is going to be charge over capacitance. If there is no charge on the capacitor, the voltage across the capacitor is also 0, which is going to be important. So immediately after the switch closes, okay, switch closes here. What is going to be the, wait, hold on a second. So immediately, so switch closes. You know what? I think I messed up on this diagram. Let me look here. Okay, no, we're fine. All right, so when the switch closes here, the voltage is going to go like this. I thought I made a mistake in this diagram. So 12-volt battery, that means that the negative plate is 0, positive plate is 12. So let's follow these volts around. So how many volts would we have right here? 0. How many volts right here? 0. How many volts right there? 0. We would say that's the electric potential. Right here, the electric potential is 0. Now, if there is no voltage across this capacitor, that means, you know, the change in electric potential, the delta V across this capacitor is going to be 0. So if we have 0 on the right, there must be 0 on the left. So let's keep following this. So 0 volt there. How many volts would we have right here? Still 0. How many volts would we have right there? Still 0. Now let's come up here. How many volts here? 0. How many volts would be right here? 0. Now, why is there no voltage across this resistor? The reason there's no voltage across the resistor is current wants to follow the path of least resistance. When charges come into this junction right there, the charges have 2 choices. They could come down the bottom path where the resistance is essentially 0. There's no resistance down here. There's a nice clean path to a lower electric potential. Whereas the higher path up here involves crossing a 6-ohm resistor. So all the current is going to come down this bottom path ultimately to charge this capacitor. The capacitor is going to start picking up charge. Now the end result here, so right here we'd have 12 volts. This is the 12-volt side. Right here would be 12 volts. So notice all the volts are across this 2 ohm resistor. The full voltage of the battery is across the 2 ohm resistor. So using Ohm's law, the current at point A, which is the current going through this 2 ohm resistor, Ohm's law, delta V equals IR. We want the current through that 2 ohm resistor, delta V over R. We have 12 volts across 2 ohms. So the current at point A, we're finding the current at A, B, and C. The current flowing through point A is going to be equal to 6 amps. Okay, how about current at B? So current at B, none of the current is going to come up here to point B because that's the path of high resistance. All of the current is going to come down here to charge the capacitor. So B has 0 amps, and then C is going to be also 6 amps. All the current is going to the capacitor. Now, as time passes, what happens is this. So, you know, current is positive charge motion. So positive charge is going to build up on this left plate, which causes the positive charges on the right plate to repel. So the positive charges on the right plate are going to leave, which leaves this right plate negative. If positive charges leave that right plate, it's going to leave that plate negative. Now, a long time after the switch closes, this capacitor is going to be fully charged. It's no longer going to be a charge of 0, and it's no longer going to be a voltage of 0 across that capacitor. So how do we go about doing this? Well, we want to find the currents again. What's the current at point A? What's the current at point B? And what's the current at point C? Okay, so a long time after the switch closes, no more current is going to come down to the capacitor. The current coming down to the capacitor is going to go to 0. And the reason why is because the capacitor is now fully charged. It cannot take any more current. This leaves the 2 ohm and the 6 ohm in series. So current comes out of the battery. I know this diagram's getting messy. Current comes out of the battery. It goes through the 2 ohm, up through the 6 ohm. None of the current goes to the capacitor because the capacitor is fully charged. A 2 and a 6 in series is 8 ohm. So the 2 ohm and the 6 ohm will have equal current. Resistors in series have equal current. And together they simplify. A 2 and a 6 simplify to 8. So let's just use Ohm's law right here. We have 12 volts across 8 ohms, so denominator is 8, which gives 1.5. 1.5 amps will be the current in both the 2 ohm and the 6 ohm. All right, so that was a long intro to this problem, but everything we just talked about we're going to use for this problem. So now let's start the problem. All right, so here is our given situation. So students are given 2 resistors connected as shown. We have a 1 9-volt battery and an ammeter. So the only equipment here, we have an ammeter, which measures current, and 1 9-volt battery. They want us to set up a circuit where we can determine, using only these 2 pieces of equipment, the ammeter and the 9-volt battery. We need to set up a situation where we can determine R1 and R2 by taking measurements using that ammeter. Okay, so the circuit you want to set up is this. So we're going to hook the battery, and you could show that. So battery, E for EMF, it's 9 volt. It's a 9-volt battery. And then place the ammeter in series like that. So this setup would allow for measurements to determine R1 and R2. Okay, so they want us to describe the experiment. So I wrote down steps. I'm not going to write this out. I'm just going to say it out loud, and if you want, you can go back and like re-listen to the video and copy these down. So I described the experiment in 5 steps. So we got to, in describing the experiment, we need to describe the experiment by listing the measurements to be taken And then also we need to explain how the measurements would be used to calculate the resistances. So describing the experiment. So my first step, I wrote, so step 1, connect ammeter and 9-volt battery in series to the given circuit at points A and B as shown. So we got point A, point B. So what we did is we connected the battery and the ammeter in series to the given circuit at points A and point B. Okay, step 2, with switch open, record reading of ammeter. With switch open, this is step 2. With switch open, record the reading on the ammeter. Okay, so current flowing through the ammeter with the switch open, I'm going to call that I-O, where O stands for open. Okay, so that's step 2. Step 3, close the switch. Step 3 is close the switch and record the new reading of the ammeter. And I'm going to refer to that current with the switch closed. I'm going to call that IC for closed, for when the switch is closed. And these two currents are going to be different. They're different current readings. So IO, this is switch open, the current with the switch open. IC is the current with the switch closed. All right, step 4. So now we're getting into how to find the resistances. So step 4, I put to find R1. To find R1, we're going to use the situation with switch closed. To find R1, use data from when switch is closed. So we want to be using the current reading from when the switch is closed. Now, if the switch is closed, we have hold on here. Okay, when the switch is closed, here is the important thing to realize. When the switch is closed, current comes out of the battery, it goes through resistor 1, and none of it is going to go up here through resistor 2. And the reason why is current follows the path of least resistance. Current is going to come down through the switch, there's no resistance there, and then back to the battery. Oh, and ammeters also have 0 resistance. So when the switch is closed, resistor 2 gets 0 current because current follows path of least resistance, which is going to be the path where the switch is. So we basically have 1 battery and 1 resistor. So if we look at this, if we look at R1, when the switch is closed, the voltage across resistor 1 is going to be the full voltage of the battery, which is 9 volts. And the reason for that, 9-volt battery means 9 and 0. So right here we'd have 9 volts. Right here we'd have 9 volts. Now do the other side. Right here is going to be 0 volts, 0 volts. Even right there is going to be 0 volts, 0 volts, 0 volts, 0 volts. We have 9 on the left, 0 on the right, 9 volts across resistor 1. So we're going to use Ohm's law here. Delta V equals I with the switch closed, R1. So therefore, resistor 1 is going to be the voltage across resistor 1 divided by current when switch is closed. So this is going to be 9 volts divided by current when switch is closed. Did they give that to us? They did. Where is it? Where did they say that? Where is it? Oh, you know what? That comes later. That comes the next part. So for right now, this is just going to be over current with the switch closed. You can leave it like that. Okay, to find R2, to find resistor 2, use data from when switch is open. So we'll say use switch open. So when the switch is open, so let's revert this. So when this switch is open, so our diagram was ammeter. Okay, switch open. When the switch is open, we have resistor 1 and resistor 2 in series with each other. So the total resistance, this is a 9-volt battery, right? So we got 9 volts here. We basically have 0 volts there, right? 9 volts here. So the voltage from this point to this point is 9 volts. The total resistance across those 2 points, if resistor 1 and resistor 2 are in series, the total resistance is going to be R1 plus R2, because that's how you simplify resistors in series. So finding R2, I would say this. I would say 9 volts, which is voltage of battery, is going to equal current switch open times R1 plus R2. And we already know what R1 is, so we can solve this for R2. So doing that, you could say 9 over I switch open is equal to R1 plus R2. So therefore, R2 is 9 over current switch open minus R1, like that. All right, now moving on to part B. Okay, moving on to part B. So now we have a second group of students, and we're bringing in a capacitor here. We have a capacitor in this circuit. One very important thing here is they're no longer using just a 9-volt battery. We're using a power supply, and this will become significant in part C. So for this part here, it says we have a power supply. So the potential difference between A and B is maintained at 9 volts. So our circuit diagram, this is a power supply, and we're going to want to be able to record current again. So that's going to be our diagram, and we'll label this E, that's 9 volts. Now, here we're actually given values. The initial current is 0.9 amps, and then after a long time it's 0.3. So this switch gets closed, and so for this discussion, I'm going to say that a subscript of 1 indicates immediately after switch closes, and then 2 is going to be a long time after. So our ammeter reading here, so I1, which is immediately after, is 0.9, and then I2, which is a long time after, is 0.3. So we have 2 different current readings. So they want us to, first of all, compare the current through resistor 1, resistor 2, and the switch immediately after the switch is closed, and we're comparing that to the currents a long time after. So I think the easiest way to do this is to make a little table so it's super, super clear. So here is a little table. So we're going to say immediately after, long time after, and then we're going to look at resistor 1, resistor 2, and then the switch. Okay, so let's start with immediately after. So the switch closes, this capacitor has no charge on it yet, right? It tells us that it's initially uncharged right here. Initially uncharged capacitor. And again, what is the significance of the capacitor being uncharged at the beginning? Well, capacitance is charge over voltage. So solve this for voltage. If there's no charge on the capacitor, there's no voltage across it. So when the switch first closes, the voltage across capacitor is 0. So 9-volt battery, 9, 0. So right here is going to be 0. That dot right there is going to have 0 volts. And then let's do the other side. 9 volt. This point right here is going to be 9 volt. Now, no voltage across capacitor. If there's 0 on the right, that means that there's going to be 0 on the left in order for there to be no voltage. So that means right here is also going to be 0. And in fact, right here would be 0, and right here would be 0, and that makes sense because there's no current going through resistor 2. If there's no current in resistor 2, there's no voltage across resistor 2. Okay, so the full voltage of the battery, all 9 volts, is going to be across resistor 1 immediately when the switch closes. So the significance of that is resistor 1 immediately after switch closes has all the current, which is 0.9, right? When immediately after the switch closes, if the current in this ammeter is 0.9, that means, you know, the current coming out of the battery, this is going to be 0.9, and then the current coming up here is going to be 0.9, and then the current coming down to the capacitor is going to be 0.9. That current hits the left plate, the charges pile up, that makes the left plate positive. Right plate is going to become negative because the positive charges on the right plate are going to leave, leaving the right plate negative, and then those positive charges that left, that's what goes through the ammeter, giving this current of 0.9 amps. So the current in resistor 1 is going to be 0.9 amps. The current in resistor 2 is going to be 0 amps because none of the current goes through resistor 2 right after switch closes. And then the current flowing through the switch is also going to be 0.9 amps. You know, it's the current feeding the capacitor to charge it. Okay, now let's look at this situation a long time after. Now, a long time after, the capacitor is going to be fully charged, which means no more current is going to come down through the switch. That's going to go to 0. The current coming down to the switch is going to be 0 because capacitor is fully charged. This is going to leave resistor 1 and 2. Resistors 1 and 2 are going to be in series now because the current, which is no longer 0.9, the current is going to come out of the battery through resistor 1 up to resistor 2 and then through the ammeter. So resistor 1 and resistor 2 have the same current, which is the 0.3, right? So this is going to be 0.3 amps through resistor 1, 0.3 amps through resistor 2, because resistor 1 and resistor 2 are in series. Okay, let's go to number 2. We're getting near the end here. Calculate the values of R1 and R2. So let's clean this up. Let's revert this back. So again, 1 means so again, 1 is immediately after switch closes. That was 0.9 amps. And then 2 means a long time after which is 0.3. Okay, so how do we calculate these values? Okay, so to find R1, we're gonna look at the situation immediately after the switch is closed. We're gonna be using this value right here. So finding R1, so we're doing this calculation right there. So finding R1, we're gonna use data immediately after switch closes. So immediately after switch closes, as we said before, the full voltage of the battery is across resistor 1 because capacitor has no voltage yet. There's no voltage across the capacitor, so that leaves all the voltage across R1. So using Kirchhoff's loop rule, which I started this video with, so 0 volts, 9 volts, let's loop this circuit. Let's start right here. We're gonna loop the we're gonna cross the battery. That's a voltage gain of 9 volts. Okay, we cross resistor 1, so the current through resistor 1, we're calling that I1. So that's gonna be minus I1 times R1, just using Ohm's law, delta V equals IR. So IR, that's the voltage across resistor 1. And then let's loop down across the capacitor. There is no voltage across the capacitor because there's no charge on it. Ammeters have 0 resistance. We're back to where we started. So this must equal 0. So we can solve this for R1. That's going to be 9 volts over I1. So 9 volts, I1 is 0.9. This gives us 10 ohms. Okay, let's do something similar to find R2. So to find R2, we're going to use data for a long time after. Use data from a long time after, which is going to be this 0.3. So the switch has been closed for a long time. When the switch has been closed for a long time, what that means is no current goes to the capacitor because the capacitor is fully charged. The current is going to pass through resistor 1 and then go up to resistor 2. We're calling this current I2. I2. So let's use Kirchhoff's loop rule. So starting right here, we gain 9 volts crossing the battery. We're going to lose some volts across R1. That's going to be minus I2 R1. And then we're going to lose more volts across the second resistor, minus I2 R2. And then we're back to where we started. Ammeters have no resistance, so there's no voltage across the ammeter. Now we have everything in this problem. In fact, we already know what this is. Wait, what are we saying? Oh no, we already know what R1 is. R1, we figured out. R1 is 10 ohms, so we can use that. So we're solving this for R2. So solving the algebra here, that's going to be 9 minus I2 R1 over I2. So this will be 9 minus I2 is 0.3 amps. R1 is 10 ohms because we just did that. And then I2 is 0.3. So R2 comes out as 20 ohms. So we got R1, R2. We're done with that part. Okay, part 3. Determine the potential difference across the capacitor a long time after the switch is closed. All right, for this question, the thing to realize, let me just revert this back so I can explain it nicely. Oh my gosh. All right, so they want the potential difference, which is the voltage, across the capacitor a long time after the switch is closed. 9-volt battery. Okay, so here's our capacitor. Switch has been closed for a long time, So the current, there's one current, which we called I2. I2 comes out of the battery through resistor 1, up through resistor 2, and then back around. There's one current here. Now, this point and that point, if you hooked a voltmeter to those points right there, you would be reading the voltage from across left point to right point. And that would be the voltage across resistor 2, and it would also be the voltage across the capacitor. The point being here, R2 and the capacitor are connected in parallel. When components are connected in parallel, they will always have the same voltage across them. So I think the easiest way to find the voltage across the capacitor is to find the voltage across R2. If we can find the voltage across R2, we have found the voltage across the capacitor, because R2 and the capacitor are connected in parallel. So how do we find the voltage across R2? Just use Ohm's law. So finding voltage across R2, delta V equals IR. The current, when the switch has been closed for a long time, we called that I2. That's going to be 0.3 amps. And we now know what R2 is. That was 20 ohms. So that gives us what? 6 volts. There's 6 volts. Oops, remind me later. So 6 volts across R2, and therefore 6 volts across the capacitor. All right, very, very last question. And this, to me, this was the hardest one. I had to think about this for a while. So we have a third group of students using the same combination, and they connect it to a 9-volt battery. So if you had trouble with this question, probably the reason why is, so the second group of students, they had a power supply that kept the potential difference between A and B at a perfect 9 volts. Whereas the third group of students, they're using a 9-volt battery that they're assuming is ideal, meaning no internal resistance, but they don't know for sure if that 9-volt battery has an internal resistance or not. So how does the third group's value for R1 calculated from the data collected compare to the second group's value? Okay, let me one last time. Okay, so here is our circuit. All right, so group 3, we're trying to find R1. So we want to do this. We want to use the data for when the switch is first closed, immediately after the switch closes. Immediately after the switch closes, we called that I1, that was 0.9 amps. So this is a 9-volt battery, but here's the thing. What these students don't realize is that this battery has an internal resistance with it, whereas the second group of students, they had a power supply that kept this at a nice, perfect 9 volts. So the third group, they have this internal resistance, which is essentially just, it's another resistor in the circuit placed in series. So how would this internal resistance affect the calculation of R1? Well, here's what we did when we calculated R1. So we looked at the situation immediately after switch closes. Immediately after switch closes, we said, the full voltage of the battery, right? So 9-volt battery, that basically means 9 and 0. So we went around and we were like 9 volt there, 0 volt there, 0 volt there, no charge on the capacitor, so therefore no voltage. R2 gets no current because current follows path of least resistance, and 0 right there. So aha, we had the full voltage of the battery across R1. So then we applied Ohm's law. Delta V equals IR. So therefore R1 is going to be the voltage over the current. Now, the reading here for this third group of students, they're not going to get 0.9 amps, right? That was the reading from the second group of students. So the third group of students, what they would do is they would say, well, our battery is 9 volts, right? Because they don't realize that there's an internal resistance there. They would plug in 9 volts for their voltage across R1. Then they would take the reading from the ammeter, and the reading from the ammeter is the current through resistor 1. But here's the deal. If there was an internal resistance in this battery, this internal resistance would make this current reading less. And if current is less, due to that internal resistance, that would make R1 greater.